Yeah, hi everyone. From me too. It's great to be here. It's great to show you some cool things, or at least I think they are cool. But I kind of feel like I'm the odd one out. First of all, I don't have a website built with design. I'm sorry. And also, I did not have any prior Zig experience before I started coding what I did for this talk. But small spoiler, I find it's awesome. I had a lot of fun building it, and I hope you will have a lot of fun watching me present to you what I have built. So as David already said, I'm going to talk a bit about a pretty different model of computation than what you might be familiar with. So maybe by show of hands, has anybody of you already heard something about constraint programming? Well, nobody. That's great. So you're all going to learn something today. And maybe write a comment in the YouTube comment section if you have heard about constraint programming. That's some free engagement there. All right, but maybe first a few words to me. As I said, I'm Lukas. I'm studying at the University of Ulm. I'm currently writing my master's thesis, and I will hopefully be finished in December. And Ulm was also where I first heard about constraint programming. I think it was in a lecture by Professor Tom Frübert, who was also the creator of CHR, which we are going to look at today. Great. So what is constraint programming? What is CHR? Many terms. They have not yet explained anything. So let's start by a quote. Typically, when you program, like for example in Zig or in other imperative languages, you kind of give the computer a manual. So you write sequential steps that the CPU executes to produce the result you ideally intended it to produce. But with constraint programming, this paradigm is a bit different. We are more specifying properties of the result we want to achieve, and the computer then hopefully figures out how to get to that result by itself. We can see this with this example. So the constraint name min kind of gives away what it's about. So we want to calculate the minimum of not only two numbers, but of a whole range of numbers. And we can read this as the following. So imagine we have a candidate that could be the possible minimum. The candidate with the number assigned to n. And then we check every other possible candidate with this constraint. And if it's greater than n, so if any other number is greater than our candidate we're currently looking at, then we just remove the second one. So as I said, we did not give a line-by-line instruction, but we said if there's any possible candidate that is, or any possible candidate that is greater than any other possible candidate, we just remove it, and at the end we will hopefully, or we will definitely end up with one correct solution. So we can identify different parts in this rule. So this one line we call the rule. As I said, we have true constraint. We call the min, that's just the name, and then we have both one variable inside them. The next we have the operation. I already said what it does. Namely, it moves here the second one. It does nothing to the first one. And then we also have a guard. This controls whether a rule is applicable. And we have I call it result. It's not really the result, it's what will be left after the rule has fired. In this case, it's just true, so that means we don't do anything at all, we just continue execution. Sure, so this backslash is not the only operation that CHR supports. We also have, for example, a propagation rule. Propagations are used to add logically equivalent new information. That can be useful, for example, if Well, I can't think of a concrete example now, but it typically is useful to just add new information and hope that more rules will be applicable if we have added this new information. But as I said, if we would read the rule in a formal, in a logical sense, the information is nothing new as it's just inferred by what's already there. Then we have a simplification. Simplifications just replace what is in the head with what is here in the body if the guard holds. We could maybe make an example where simplifications would be useful. We can see that when I write here.
You want to write here?
But then it would destroy the beautiful logo.
That's okay.
Okay. We could imagine having different constraints that represent like north, east, west, and south. And if we want to simplify our bucket of constraints, we could have a rule that reads like, I don't know, west and east, and that would be just simplified to true because they cancel out each other. That's like a typical example for simplification rules. And lastly, we also already have seen simplifications. We don't do anything to the first constraint, but we remove the second constraint in the head if this is often used to get rid of maybe duplicate information. So imagine we have two west constraints. Then the second one here is kind of irrelevant. We already know this information, so we can just remove it. Great. You might already have noticed that both propagation and simplification rules are basically expressible with only simplification rules, because simplification can keep constraints and add new ones, but also can remove constraints. So if we will later look at what I implemented in Zig, we will notice that the implementation or the embedding of CHR into Zig only uses simplification rules. And if we would, for example, express a propagation, then we would just keep the removed head part empty. So this part would be the empty set and would not remove anything. Just a small optimization. Maybe we can look at this right now so that you get a sense of what I implemented. Is this big enough? If we go to, maybe we go to the rule solver, there should be a propagation method. Yeah, and you can see exactly what I said before. We just call it simplification and pass an empty head where we would have removed constraints. And the same goes for simplification. But I think we will take a deeper look at the code later when I actually have explained a bit more. All right. Then, what is actually the head and the guard and the body of the rule? The head always contains constraints. Like in the min example, the min constraints. Those are CHR things. There's no such concept in Zig. So constraints come from CHR. The guard, on the other hand, contains I call it conjunction of built-ins, but a built-in is basically Zig code. So in the guard, we can run arbitrary Zig expressions to determine if the rule is applicable. In the guard will never contain any constraints. And the body can contain both, so we can return new constraints from the rule, but we can also execute Zig code. And that kind of makes CHR a cool thing. It's not on its own, a formalism on its own inside of Zig, but it combines the host language together with the formalism. And well, at least I think it's pretty cool that we can bring such a concept to other languages. All right. Then next, maybe we look at what the spin example looks in action. I already told you some theoretical stuff, and you already have seen this example, but you didn't see how it actually works. So for that, we start with the following query. So we want to determine the minimum of the numbers 3, 1, and 5. I hope it's obvious that 1 will be the answer, but how does CHR find them out? We start by adding constraints to solve for. So this is the query. I already added them. The next, we just go through them from left to right. And we start with the min3 constraint, and we make this one active. And active means that we now try to find a rule that can be applied on it. Yeah, that's sad. We only have rules that need 2 constraints, and we only have 1 active constraint. So we do not find any rule for min3. Yeah, we could try it there, but 1 always stays empty. So it moves alone inside the constraint store and waits there until somebody else needed it. The next, we check min1. So that's just the next constraint inside the query. We now also notice that 1 here stays empty, but we remembered that min1 is already in the min3 is already inside the constraint store, so we just can take it. And in this process, n and m get bound to 1 and 3, so now we can evaluate the guard, and we notice that 1 is indeed smaller than 3, so this rule can now fire, and we remove min3 from the store and write back min1. All right, so lastly, the same process for min5. We also try to find a matching. You might have noticed that min1 went to the first constraint, and min5 went straight to the second constraint. That doesn't really matter. I just put it that way so I have less animations to write. But we can execute this with my embedding and see actually that it doesn't matter in what order they are checked. All right, so min5 also noticed that the first constraint is still empty, so we can again take min1 out of the store, bind n and m to 1 and 5, check if the guard holds. Here it does hold. So min5 gets now removed. Okay, that's not much work since it wasn't present in the constraint store to begin with. And min1 gets added, but again, not much work since it's already in there, so nothing changes. Now our query is finished, so we have no more constraints to check for. Thus, we are finished with our whole computation, and what's left inside the constraint store is our final result, and we can see that 1 is indeed the minimum of 3, 1, and 5. Yeah, so I hope this made it a bit more clear how this computation works. And now, what would happen if we could not find a minimum? So we could also think, or maybe think of a different algorithm that does not produce a result. How could we like notate failure? We will just return false and not true. Then in the end, false would be in the constraint store, and this would indicate a failure of our program. But maybe in contrast to other logic programming languages, like, I don't know, does any of you know Prolog? Yeah, more people. So Prolog does backtracking when it encounters a failure. CHR is committed choice, so we don't backtrack and try other rules. When there's a false, we're just done. All right, enough with that. Let's take a closer look, or a first look at the embedding algorithm. So how do we get from this to a rule to executing it in Zig? there's, lucky for me, a paper called FreeCHR, which describes the process. This is also co-written by Professor Frübert and Sascha Rechenberger, who also both work at Ulm University. And I pretty closely followed what was described there. But to be clear, FreeCHR is not the only way one can embed CHR in different languages. I think the paper is also only like a year old, and I know of a Java implementation that takes a completely different approach to what I did. But FreeCHR aims to standardize the embeddings process so that embeddings could be easier maintained, and it's just a bit nicer to implement them. I also said that every rule is implemented as this implementation rule or for tuple. We also saw this in the code. And generally, a program is composed of multiple solvers or rules. Maybe it's smartest to also show this inside the code. Just a second. So I organized them all inside this solvers directory. And when we look at the interface they all have to implement, they basically just implement the solve method, which gets a state. The state contains, for example, the constraint store we saw earlier in the example, and an active constraint that would be the current constraint from the query we are trying to fit. So we then have a rule solver that, as I said, implements the solve constraint, and a rule solver models a single rule. So the single rule that computes the minimum would be modeled by this solver. I can also show you this in a second. This would look something like this. There we also have one simplification rule and then just our constraints. We can look at this example in a few seconds. But if we have a program that consists of more than one rule, there's another solver, namely the composite solver, that that takes a list of multiple solvers and just tries them one by one. So this way we compose more complex programs just out of single rules or single solvers. Great. You can also find the code I wrote on GitHub, or you can go to zigtoberfest.fun, which I rented already, which will redirect you to a place where you can find the slides and the code. So if you would like to, you can have a look at it. Please do. I don't want to have spent like 10 or 15 euros for that domain for nothing. All right. But the title of my talk was Exploring Properties of Constraint Program, and we have yet not looked at any properties. So let's start with that. Anytime is one of the simplest and maybe a bit useless, or at least I could not find a practical use for it. But it describes that a program can be interrupted at any time, and if we then look at the current state, we will always get a correct approximation of what the final result will be. This could be useful, for example, if we have like time constraints, when our algorithm has to be finished in, I don't know, 2 milliseconds, then we could just stop the execution at that point and take what we already have computed as an approximation of our final result. We could try to also look at that with the embedding. That was the wrong key combination. Just a second, I need to restart the terminal. By running, let's see, build min, we can execute the min example I just showed you, and we can pass. We had 5, 1, and 3, I think. And you can see that the embedding also calculates the correct value, but if we want to take a more closer look, I think it was the log to show what it's actually doing. Just a second. Yeah. Maybe we just, for a second, we could step through this logging stuff. We can see that it also starts by just adding the 3 constraints to the query. It then takes one and tries to find a rule. It could not find a rule that is applicable, so we add it to the store, then we take the next one. Now we actually do find a rule, so we try to execute it with 1 and 3. That does work, so we remove 3 from the store and continue this way. But what I actually wanted to show you was the constraint store. I'm not sure what the option was. It was the store. Then this will print out the constraint store at different time points in time. And you can see if we would just, I don't know, stop here, then 3 would be in the store, and 3 is not the correct answer to our original query, but it is at least more correct than if 5 would be in the store. So this is how I think about the approximation property. All right. The next one is a bit nicer. In my opinion, it's memorization. So you all have implemented the Fibonacci sequence, probably kind of like this. We have two base cases for 0 and 1, where we just return 1, or we bind 1 to n. And then the more general case executes the same algorithm recursively for n-1 and n-2, and the results is the results added together. I also implemented that one, but unfortunately not in my own embedding inside Zig, because my embedding does not yet support constraints with an arity greater than 1, which is not a limitation of free CHR, but just of my skill. But with like a week of more development time, this could be easily implemented. So therefore, I implemented it inside of Prolog, which is the go-to CHR embedding. So that's roughly the code we just saw, and we can also execute it with... Right, so let's say we want to calculate fib for, I don't know, the 10th Fibonacci number. It's apparently 89, I just trust that. But if we now try to calculate the 100th number, we can see that it takes a really long time. Why does it? Well, we're computing, for example, the 10th Fibonacci number a whole lot of times, and we do not remember that. So how could we change the rules so that we would remember that? This is like a common like quiz where you have a math formula laid out with little sticks, and you have to change like 3 to make it correct. We can also do this here because we only need to change 3 characters, namely this, and this one. If we change this from a simplification rule to a propagation rule, we don't remove the constraint that contains our intermediate answers, but keep them inside the store and can then use it for future computations. This way it's way faster. I also, you see it's still not done. I implemented it down here. Yep. So you can see I just changed like the 3 characters here, and I added an additional cleanup rule at the top, but that's not strictly necessary. But you can see we again use the simpagation rule to do a cleanup, just like we did with this easy example at the beginning. Great. So if we terminate that and start again and use now fib2 to calculate the 100th Fibonacci number, it's instantly. And we could even try to calculate the 1000th Fibonacci number. And you can see, for a small example, that we keep all intermediate results and we like end up here and want to calculate the, I don't know, 8th Fibonacci number again. We only need to look inside the constraint store and do not need to compute it from scratch again. So I think that's pretty cool and really easy to implement because CHR has this memorization concept or the concept to store intermediate results like baked right into it. This is also useful for example calculating distances between strings. So you might know the Levenstein distance. There you can also use this memorization property pretty easily with CHR. Oh, I'm already over time. No worries. Okay. Then next, maybe we start again with a little quiz. So imagine those two rules. So we throw a coin, and a possible result is that it leads to head, and a possible result is that it leads to tail. Does any of you see a problem with these two rules? Yeah.
If we run the same query multiple times, you might get results.
Yeah. Yeah, exactly. That's exactly the problem. So our rule order matters. But it should not matter. Independently of how I arrange my rules, we should always get the same result. Yeah, that's great for coin tossing, but for determinism, not so much. Then the second example I brought is called destructive assignment. So what we have is like a constraint that wants to assign a value to a key. And we have like a constraint that represents a memory cell storing a value for the same key. So if we now got both constraints, this will result in the same key, but the value gets overwritten with the assign or set constraint. Now imagine the following query. We have one cell containing 0 for x, and now we want to set first time 1, and then the second time we want to set x to 2. Now the rule order does not matter since there's only one rule, but it matters in what order we execute the constraints. So if we start from behind, then 1 would be the final value contained inside of the cell. But if we start from the beginning, then 2 would be the final value inside the constraint. And that's also bad for determinism. And that, by the way, is a kind of informal proof why it's often so hard to write concurrent programs in imperative languages, where this destructive assignment is baked into the language. But in the declarative world, we consider this as bad. And we don't want to rely on constraint order. If now both those problems do not appear, so if our rule order does not matter and the order in which we apply constraints does not matter, our program is confluent. So we can think of confluence being a function between our initial state and our final state. And it's always constant, it does not change, no matter how we execute it. And being confluent gives us some cool properties for free. Maybe I'll skip that for time's sake, how to achieve confluence. Or maybe not, the example is pretty simple. So imagine if we have this propagation. It looks like the coin tossing example where we propagate from A to B or from A to false. we result in those two states that are not joinable because false is not equal to B, obviously. And now to make it confluent, we could simply add a third rule that would propagate B to false. And now those two states would be actually the same, so we have achieved confluence. This is cool, but does not always work out. So if we, for example, those two rules, then this could obviously not be confluent. And even if programs can be made confluent, we have to be aware of our semantics. So the destructive assignment example from above would not be or would not work the same way if we require both values to always be the same, which would make the program confluent, but would totally screw up our computation. All right. Maybe questions, any questions to Confluence? This was maybe a bit fast by me. Yeah.
I'm not sure, but is there some way to do static analysis and determine if a program is confluent?
Yeah, absolutely. So for terminating programs, we can always determine if they are confluent or not. But how we would do this, we could prove it like this. So we would determine a state or a set of constraints that would be needed to fire both rules, and then we check to what states we get from those set of constraints, and as I said, we would then check if those two states are again joinable. It's a way more complex than what I described here, but that's roughly the case. So we find a common set of constraints which we can execute both, and then we check if the results are logically the same. And as I said, this can be done for any program that does terminate. More questions on that? Yeah.
Just in general, if the input is very large for that, like in the probability of this confluence is just taking super long, is it still then try to? Or is there any limitations that the has?
Well, the limitation would be if you can solve a more complicated problem, if you can figure out, if you can draw this diagram for a lot of rules and a lot of constraints, then there's no limitation. So this is a manual proof. We don't do this automatically. Does this kind of answer your question?
Okay. You have to do it manually. There's no automatic process, or no scalable automatic process to prove general confidence for any program.
Well, you could probably implement it, but I'm not sure how it scales. Sorry. All right. More questions? Then we can check out what other properties Confluence leads to. First is, I call it incrementality, which sounds a bit weird, but algorithms that are incremental are often also called online algorithms, which means that we can just add more constraints on the fly, and they will eventually participate in the computation, and we will get a correct result. This can be useful, for example, with feedback loops, where we get a constant stream of new informations. We can then just feed those new information constraints to our solver, and they will be part of the computation. Then the next is parallelism, which is pretty awesome because every program that is confluent can be trivially parallelized. So we do not need to think about any critical path we need to avoid or we need to lock. We can just, part all constraints into two buckets and then execute one bucket on one server and the other bucket on another server. I also have a little example for that. By the way, parallelism, or this easy way of parallelizing a Confluent program, is mainly because Confluent programs do not have this problem with destructive assignment. All right, so are you all aware, or do you all know the map reduce pattern from distributed computing? Great. So we just have a set of data, we split it up, execute different map operations in parallel, and then execute different reduce operations in parallel. We can also implement this pretty easily with CHR. We could think of a map constraint this way. So we store any operation inside our map constraint, and we store just data inside of a constraint called V. So now if we have a map constraint and we have some data, we then take this operation, execute it on X, and store our result in R, and then just return a R constraint with the result of the map. So that's our first stage for map reduce. The second would be reduce, where we also have a operation inside the reduce constraint and this intermediate result from our map stage. But now we need two intermediate results because we want to accumulate those. We then again call operation with our two intermediate results and bind the final result to R. Now a possible query could look like this. We want to map a square function and we want to reduce with an add function, and we just want to execute those two on 2, 3, 4, and 5. And then in the end, after we have done that, we still have those two constraints inside the store and our final answer, our final reduced constraint with 54, which is hopefully correct. And again, we could again prove that those two rules are indeed confluent, but you can also trust me. And because of that, we can easily partition them across a whole network of computers. Yeah.
I'm trying to wrap my head around that. When you do things in parallel, don't you also need multiple constraint stores?
Yeah, absolutely. But we can just
Do they convert?
What?
Do they convert to the final store? How does that?
Yeah. So we could, if I just go back to this diagram, we could think that maybe at this point we have on one machine we get like 3 constraint stores in, and then we again execute our program on that on one machine, and this will then produce our final.
Okay, so you don't optimize for number of operations.
Yeah. All right. I also have this one implemented. Also, unfortunately, not in my own embedding, because it does not support constraints of different types. Not yet. I'm working on that. But maybe look at it quickly. Yeah, just the same rules we just saw. Can I copy it? No. Map square reduce add. Sorry, typing is hard, man. And I call them V. 2, 3, 4, and 5. Thumbs crossed that it works. Yeah, we get the 3 constraints we also saw in the slides and our final result. We could also remove some, and it obviously still works. Great. Originally, I wanted to show you some cool patterns that we could apply to those two rules, but looks like there's not much time left. But we can talk during our meal at the end, if you still want to see them. Yeah. Did you have a question? Sorry. So, yeah. What? Maybe the last question you have is, why should we use this? Obviously, you don't have to. SIG works as it is perfectly fine. But as I said in the beginning, I think it's pretty cool to like merge those two really different ideas. So the idea of constraint programming, where we ideally do not have side effects, where we don't have destructive assignment, and on the other hand, Zig, which really tries to produce optimized code with a lot of side effects. And I mean, not everything in life has to have a valid business case behind it. I think this was mainly fun for me to implement it and play around a bit with, first of all, the like theory behind this free HR embedding, and then see how it works and if it's any good. Yeah.
There is one more use case too.
Yeah.
I do in my free time a lot of reverse engineering, and I use the Z3 solver for figuring, for example, some flags like CPS and so on. And that's a very valid use case for constraint programming.
Yeah.
Just want to add that.
Yeah, great.
Yeah, thank you very much, both of you actually. Because that was my question, if you could make like a more concrete example to use this.
I can name a whole lot of concrete examples. So, for example, in timetabling, constraint solvers are often used, or in general in any optimization problem. It's always.
There's also, I think, sort of auto layout, maybe, for the old Apple UI around the system. That one also was constraint programming.
Another example is like in fuzz testing, it's pretty useful for determining like if you would like to hit a specific case and you sort of permute your inputs, and like for example you have the size of the item that you generate and size of the block, and you would like the one of the item to fall like between the blocks, basically like in on the bit spread. And it would you say that okay, these are my sizes, generate me something that would hit for the bit block. And very similar to whatever you probably for security. The other people use it for correctness, but it's like the opposite side and the adversarial.
Yes. CHR is actually also often used to prove semantics of other rule-based programming languages. So you would embed those inside of CHR, which is kind of Inception-like, like an embedding inside of an embedding, and then use CHR semantics to prove the semantics of another language. Yeah. So what's left to say? I thought Sig was pretty awesome. I had a lot of fun implementing and fiddling with it, and I hope now you think that constraint programming can be fun too. Yeah, thanks a lot.
Will you show the slide with references once again? Use
Yep.
it over.
Sure. So this is just the free CHR paper which I showed. That's a book. I also have it with me, so if you want to take a short read. Yeah.
Can I make a brief comment?
Yeah.
Lukas, I have some beta plans for you. So, backup radical. So,
Yeah.
can you bring up the zbuild terminal? The terminal where you run zbuild earlier?
Yep.
Yeah.
Oh, did I close it? Looks like I closed it.
Yeah, you probably.
You don't
I
have the
don't
build
have to go
file.
for it. It's basically for you to see there. Yeah. So you run zbuild here, right? And you didn't remember all the
Yeah.
command line arguments. Yeah, you can run zbuild-h. This is not really enough. This is just the start. So
Does it also show them here? Ah.
it also shows your
Right.
project specific options.
Ah,
Now,
cool.
so here's the right idea. I cannot promise your professors will like this idea or understand it. But in my university, I've seen a lot of very interesting projects that implement like these algorithms and ideas, and they're all usually completely unusable. So here's the radical idea. Write your implementation in Zig. If there's an interesting C solver, link it, make it usable from Zig. If you want users to be able to write constraints in like not as Zig source code, but like as a plain text file kind of thing, write a parser for it, a good one, a three-seater grammar to syntax analytic, a language server that gives feedback to the user, and then also compile your software to WebAssembly and make a playground on your website. You have one?
I don't have one, but
But you're working it?
there exists a JavaScript embedding which has
Yeah, no,
a-
fuck that.
but just for the sake of completionist, you can go to not focused. Can go to chrjs.net, and there's a playground where you can input your.
You can make a 10x, 100x better. Here's another radical idea. Embedded is a database plugin in an existing database. So the users push constraints as rows in their database or whatever the database is. And then they can run a database query to obtain a constraint result. Like things like permission systems, I think would probably be a great fit for that. I guess my point is, this is probably not a path to academic success, I suspect, but there's an interesting angle on actually making these things usable that never gets explored in university, ever. Just putting it out there. And Zig is probably an interesting tool to get that on reasonably well. That's it.
Maybe some positive feedback. It absolutely was.
When you finish your master, do you plan on like staying at university?
Yeah, I would love to, but it's currently not.
That's actually bad news for this project. Once you're free, you will find.
Right. So if there are no more questions, I think I'm done with like 20 minutes over time.